23, chapter 23, set B. We're only going to do the first 6 problems. So number 1, we have a list A and a list B. Match each phrase on list A with one on list B. Population. Population is the same as the box. Good. Population average. Average of the box. 420. Sample. Draws. Sample average. Average of the draws. Sample size. Number of draws. Now, if we know the population and we're going to make draws from that box, what can we do with that information? If we know the population and we're going to make draws, what can we do with that if we know the population? Yeah, along those lines. So if you know the population and you are going to make draws, what sort of, you would use probability. So if you haven't done the draws yet, you know the population, you can calculate probabilities. If you don't know what's in the box and you make draws, then you can create confidence intervals to figure out what you think is in the box. 2. In each pair of phrases, one makes sense and one does not. Which is which? Explain briefly. A, SE for box, SD of box. So, which one doesn't make sense? Finding the SE of the box or the SD of the box? Why does the SE of the box not make any sense? SE is dependent on how many draws. The SD of the box is calculatable, or you can estimate what it's going to be, but you can't take the SE of the box because the SE relies on the draws, how many draws you make. Okay, B, SE for average of the box or SE for average of draws? Can you take the SE for the average of the box, or can you take the SE for the average of the draws? Average of the draws for the same reason, right? The box has an SD. It does not have an SE. SE is linked to the number of draws. Right, Alexis? 3. For the income example on 415 and 417, the SD of the box is estimated, or about 53,000. So we don't know the SD of the box. So we take the SD of the sample and we pretend that it's the SD of the box. Okay, B, the SE for the sample average is about or estimated at 1700. And the blank value for the sample average is observed. Why is that one observed? Well, you're not given the population. So if we right, if it's not the actual number in the box, then it has to be an observed value or an estimated value. But we didn't estimate that. We actually did it. So that is an observed value. And hopefully it's pretty close to the actual value. Okay? Oh, they even had words down below that. Oh, estimated. Huh. I didn't even see those. Number 4. In example 3, suppose 50 different survey organizations take random samples of 400 persons aged 25 and over in the town. Each organization gets a 95% confidence interval by calculating sample average plus or minus 2 SE. How many of these intervals should contain the population average? If they do 50 of them, two. So what they're saying is, here is the true average. Okay, we don't know what that is. 50 people are going to make confidence intervals. How many of them are right? 95% of 50, which is 2.5. Right, it's right, 5. Oh, I see what you're saying. Yeah, 5% are wrong. So how many groups are right? 47 or 48, right? Because it's 2.5. Yeah. Does everybody understand that? Okay. And then that's actually shown on the next problem. The figure below is a computer simulation of the study described in exercise 4. The confidence intervals are plotted at different heights so they can be seen. Why do the intervals have different centers? Okay. Um, it means different observed values, right? If everybody does the same study, my average and your average will probably be close, but they're probably not going to be the same thing. Well, it's a plus or minus 2 SEs. Right. So what it's saying is, so what are all of these blue lines? They they are the observed averages, right? Of their particular study. So why are those observed averages different? Because they're observed averages, right? There is going to be some chance error, some mistake in the sampling procedure. Okay. B, why do they have different lengths? Well, they have, because they have different SDs. That would be the answer. Okay. So a larger SD is going to create a larger interval. Right, Joel? Okay, and C, how many of them cover the population average? So are there really 50 of them there? So we just count the ones that miss. I only see one. There's only one that doesn't hit it, so 49. Is that what we expected? It's pretty close, right? We said 47 or 48, and we got 49. Yeah, that's pretty close. If we would have got 46, would we have been surprised? Nope. 46 and 49 are equally likely. If we would have had 35, would we be surprised? Yeah. That means something's wrong. 35 is just totally impractical. Okay, number 6. A university has 30,000 registered students. As a part of a survey, 900 of these students are chosen at random. Their average age of the sample turns out to be 22.3 years with an SD of 4.5. So the average age of all 30,000 students is estimated at 22.3 years, and it is likely to be off by, is it 4.5? Why is 4.5 the wrong number? Well, so we had 22.3, that's my X bar, and my SD is 4.5. But we don't, the SD does not bring in chance error. We need the SE average. Right, we have to divide that by the square root of 900, which is 30, 0.15. Okay, so 22.3 plus or minus 0.15. Why is this number so small? 900 draws is a lot. So we're pretty sure 22.3 is very accurate. because we did 900 draws. If it's a truly a simple random sample and we do our sampling correct. Right. Okay. Find a 95% confidence interval. So we're just going to add 0.3. So 22.0 to 22.6. Is everybody okay with that? Create a 95% confidence interval. This is B, right? So I doubled that. No, I doubled it and I added it and I subtracted it. Okay, that's it.